Okay, second half of the spectra lesson. So we looked at how atomic spectra form, which is an important exam question. Let's just have a look at a couple of the other things that are associated. So this picture is very familiar with you because I have a big version of this up on my wall. Every element has an individual spectrum in the visible spectrum. They also have spectra that extend into the ultraviolet and the infrared that are unique to them as well. But it's a unique fingerprint for each element. And as I said to you when we first started this topic, scientists had spent a lot of time trying to understand how this fingerprint formed and trying to come up with some maths that did the job. And our maths for the energy levels of hydrogen pretty much perfectly explains the emission spectrum of hydrogen. So you can probably identify H alpha, H beta and H gamma on the top line of that picture, and then there's 4 more, and those 4 more are the extra energy levels that we didn't bother trying to squeeze into the diagram and we didn't bother doing the calculations for. But H alpha, H beta and H gamma are the ones that tend to dominate spectra when you're doing astronomy, and we'll come back to that when we do the extra part of the topic. But of course every single element has some electron transitions which exist within the visible region. It gives you these fingerprints that you can see in front of you. I've shown you a neon discharge tube, and you can see all of the red lines there for the neon. And so the fact that neon is very efficient at turning electrical energy into red light is why neon tubes exist. You remember having a look at the sodium. You can't actually see there that you've got 2 very narrow lines in the yellow on the sodium. It looks like you've got 1 yellow line and 1 green line, but actually you've got 2 yellow lines and 1 green line. You've got 2 yellow lines, 1 green line and 1 green blue line. You should be able to see 4 lines there, but the yellow isn't. The resolution is not good enough to split the yellow into 2 visibly. And then mercury. Now it looks like mercury from that image looks like mercury does a lot of discharge in the visible, more so than say sodium. But if you were to compare a sodium discharge lamp with a mercury discharge lamp, you would find that sodium was much more efficient at producing that yellow light when we put electricity through it than mercury is at producing like yellow or red or blue-green or blue when we put a discharge through mercury. Turns out that mercury is actually very efficient at producing light in the ultraviolet, and we'll come back to that later on. So they're there because they're the very common discharge tubes. Hydrogen because it's simple, helium similarly simple, neon because it's very efficient at producing red, sodium because it's very efficient at producing yellow, and mercury because it's technologically important. And the important thing about an emission spectrum is that it has very narrow lines, effectively infinitely narrow. There's a little bit of thickness to them because of Doppler shift, but effectively infinitely narrow. And they are fingerprints, particular to particular elements. And sometimes you get exam questions which ask you to explain that. So, explain why atomic spectra are discrete narrow lines at certain wavelengths. So this would be an exam question. And in the past, in lessons, I would spend a lot of time on this exam question with you. I don't have that time right now, and you aren't in front of me. So do make sure that you understand what I'm going through here, even if you have to play it a couple of times, and do make sure you've taken notes on it, even if you have to pause it and write the notes down. Okay. Atomic orbitals can only exist at particular energies. That's the Bohr model of the atom. Atomic orbitals can only exist at very particular energies. These form energy levels which the electrons can transition between. The gaps between the levels are also at very particular energies. If the levels themselves are particular, so the gaps between the levels are particular. Seemed unnecessary, but you have to say that. When an electron de-excites to a lower level, a photon is released. That's how the electron gets rid of its excess energy. It releases a photon. Oops, press 2 buttons. And of course, the energy of that photon is described by E equals hf. and you can just put E equals HF in brackets in your answer to the question, and you've ticked a box on masking. Because the energy involved is discrete and particular, so the photon energy, the energy of the photons that are produced, is discrete and particular. And so therefore, its frequency and its wavelength are particular. And that's the key point there. I'm not sure I read it out very well. Hopefully I wrote it a bit better. We've got these electrons transitioning through very particular energies, and as they lose that particular energy, they fire out a photon. The photons therefore have that same particular energy, and if they've got that energy, then they've got that frequency and that wavelength. That's the key point that you've got to try and get across to the examiner when you write this stuff out. Consequently, only photons of certain wavelengths can be released, and that produces your characteristic emission spectrum where you have narrow lines at certain wavelengths. Okay, that's not the best I've ever done with that, but you'll forgive me, I've got COVID. Right, how does the atom become excited? Well, there's a few ways. In astrophysics, quite often it's that the atom's actually been split apart. We've given our atom enough energy to ionize it, to break the electron away from the proton. So we've given it more than 13.6 electron volts. But in space, of course, there's not a lot there. So what tends to happen is eventually an electron finds its way back to a proton, and the hydrogen reforms. And it usually does not reform in ground state. It normally reforms in an excited state and then drops down through the energy levels, emitting photons as it goes to get back down to ground. And so we get the emission spectra of hydrogen in astronomical processes because the hydrogen's been ionized. And you need to make a note there. I don't think I've made a note on the text here, but you need to make a note there that ionization in physics is that process of giving it enough energy to break an electron, enough energy to break away from the atom, giving it enough energy to get past the infinite most energy level. And of course, if you give it any more energy than that, that's fine. That extra energy just goes into the Ke of the electron as it leaves, a bit like the photoelectric effect. You've got to give it enough for it to escape, and if you've given it enough to escape, any extra goes into Ke. So one way is ionization, and then the atom reforming itself after it's been ionized. How else could you do it? Well, of course, you could hit it with photons. And have it absorb those photons up to higher energy levels and then drop back down again. Trouble with that is you have to hit it with exactly the right photons, because our hydrogen can only absorb those photons that have energies that exactly match the energy gaps. Excuse me. Because any other size of energy, well, what do you do with the excess energy? You can't absorb some of a photon. A photon is a single entity, so you can't absorb a bit of it. You've got to absorb the entirety of the photon. And so actually atoms aren't very good at absorbing photons. Photons and atoms have this bit of a tendency to ignore each other, do a bit of scattering maybe, but not actually interact, because only those atoms that have exactly the right frequency to have exactly the right energy to match an energy gap can be absorbed by an atom. All other photons tend to be ignored. So photons are not the best way to get it excited. And then, of course, what tends to happen is the same photons come back out again when the electron de-excites. So not normally the best way to do it. Again, does happen in stars, and we'll come back to that when we do astrophysics. So how does the atom become excited? Well, the normal method, and of course you've seen me do it a couple of times in the lab, is to apply a high voltage to a low pressure gas tube. And that's called a discharge tube, and I've shown you a few discharge tubes. And so our atom becomes excited through collision with an electron that has been accelerated by an electric field. So it gets a little bit hard to get your head around sometimes when you're having to describe this, or when I'm describing it to you, because we've got the atoms, we've got the electrons that are internal to the atoms, and they're being pushed up to higher energy levels, they're being excited. And then we've got the electrons that are free, that are being accelerated by the electric field and are crashing into the atoms. And those two electrons are totally separate from each other. We've got the free ones that are being accelerated, that are smacking into our atoms, and then we've got the ones inside our atoms that are being excited or de-excited. And so you've got to keep those two populations of electrons separate in your head. If you confuse them, you confuse yourself what's going on, and if you're having to write this out for an examiner, you confuse the examiner about what's going on. So try and keep the external free electrons separate in your head from the ones that are internal to the atoms. And for God's sake, don't start thinking about metals when I say free electrons. Okay. So in our desk tube, electrons are either emitted from a hot cathode, and there are hot cathode discharge tubes, or just by random ionization. Randomly there's going to be the odd electron kicking around in our tube. It just is. And as soon as we've got some electrons, those electrons are going to be accelerated by the great big voltage that's across there, by the big electric field is the proper terminology, by the great big high voltage. And these electrons are accelerated to high energies, to high kinetic energies by the field. And of course we know the maths for that. Every volt gives us an electron volt. So our electrons are accelerated to high KEs by that high voltage. And then they smack into the atoms. Now, there's a couple of choices. If the electrons, when they smack into the atoms, don't have enough energy, if they don't have enough energy to promote an internal electron up to a higher energy level to excite the atom, then they'll just do elastic collisions. They'll just bounce straight back off again elastically. And you're told in mechanics that elastic collisions are theoretical, they don't really happen. But of course in particle physics they really do happen. Elastic collisions are actually the most common things that go on. Because when we're talking about single entities, atoms, how can an atom absorb any energy other than by being excited? It just can't. It's not like a rubber ball that can get hot. It can deform. An atom can't do any of that. An atom can't get hot. Heat only makes sense over a huge collection of atoms. So elastic collisions are actually the norm here. But if our electrons have high enough energies, they'll do inelastic collisions. They'll transfer some of their kinetic energy into the internal energy of the atoms. They'll excite the atoms, or they may even give it enough energy to ionize the atoms. That ionization of the atoms, that gives us a cascade where you'll get one electron hitting something, creating more electrons that hit more things that give us more electrons, and that's how a GM tube works. We'll touch on that again when we do nuclear. But right now, inelastic collisions tend to excite the atoms. And it only works at low gas pressures, because otherwise the electrons are hitting too often. And if they're hitting too often, they just never get up to speed. If they're always bouncing back off the atoms, then of course as soon as they bounce back, they're then working against the high voltage supply, which has to slow them back down again and send them back the other way, and they just never get up to speed. So that's why there's a vacuum pump in this picture. That's why these discharge tubes are always low pressure, and sometimes you're asked why they have to be low pressure. And there's a proper term for what's going on. The average distance travelled by the electrons between collisions is called their mean free path, and I've seen one exam question where you were actually asked to know that term. I did some more research on mean free paths when I was in Sheffield working on plasmas. But as I've seen one exam question where you're expected to use the term the mean free path. It needs to be a low enough pressure for the mean free path of the electrons to be long enough that the electrons are accelerated up to high enough kinetic energies to actually cause the excitation. Whew. Hope that made sense. Again, I've seen 1 or 2 exam questions on this, so you need to make sure you understand it. You need to make sure you've made notes on what I've written here. Right. What kind of questions do we get for this? Well, let's have a look at the question. What's the minimum speed an electron can be travelling at when it collides with a hydrogen atom if there is to be a chance of a visible photon being released when the atom subsequently de-excites? Now, this is probably harder than a question would be in an exam, in that I'm expecting you to remember something about the photons emitted by a hydrogen atom that the examiner probably doesn't expect you to remember. Hopefully we only talked about the photons coming out of a hydrogen atom yesterday, so you do remember. What is it I want you to remember? Yeah, as I thought, just like a lesson, you're all sitting there staring at me blankly. But hopefully somebody remembers that in order for us to get a visible photon coming out, we've got to go higher than n equals 2, because we only get visible photons from transitions down to n equals 2. Transitions down to n equals 1 produce ultraviolet photons. Only transitions to n equals 2 produce visible photons, and so we've got to promote our electron within our atom to higher than n equals 2. That means the minimum that we can promote it to is n equals 3. Woohoo. So once it's at n equals 3, then when it de-excites, we've got a chance of it producing a visible photon. And now we've also got a good chance of it just producing an ultraviolet one, going straight back down again. And of course, as that's a bigger jump than going from n equals 2 to n equals 1, that means it's even deeper into the ultraviolet, where n equals 2 to n equals 1, I think it was 122, wasn't it, nanometers we worked it out at. This one is clearly going to be shorter wavelength than that. This will be, whatever it turns out to be, 90 nanometers or something along those lines, getting into quite hard ultraviolet. So it could do that, but it could also drop from 3 to 2, and then subsequently from 2 to 1. So it could come down in steps. And therefore, if we are able to promote our electron to n equals 3, then we can get the chance of getting a red photon out, a visible photon, our H alpha, the n equals 3 to n equals 2 transition. H alpha, you've worked out what its wavelength is, so you can all shout at the screen now and tell me what its wavelength is. Yeah, as I thought. It's probably only the 3 girls who are bothered to do the calculation, so they're too quiet to be shouting at the screen. Hopefully somebody's telling me it's 656 nanometers, and hopefully I've remembered that right. Anyway, none of that matters. Or the only thing that matters here is that we know we've got to get our internal electron to jump from n equals 1 to n equals 3. So how much energy does that require? That requires 12.75 electron volts, but of course we don't do calculations in electron volts, so we've got to do that in joules. So in joules that turns out to be, hopefully I've done my maths right, I haven't double checked it, 2.04 times 10 to the minus 18 joules. Now, this is the minimum kinetic energy that the external electron colliding with the atom can have. I mean, actually, we recognise that's not true. It's got to have quite a bit more than that, because this would mean that our electron was hitting our atom and absolutely stopping dead, because all of its Ke has been transferred internally to the atom, and that's just not possible. We've still got to conserve momentum. We've still got to do all the other things that physics requires, and our electron stopping dead and our atom stopping dead. No, I don't think so. But for the purposes of the question, we can assume that all of the Ke of the external electron goes into exciting our atom. That means I can say that a half mv squared is equal to 2.04 times 10 to the minus 18 joules, and rearrange. And I get a velocity of 2.3 times 10 to the 6 meters per second, which seems incredibly fast, 2.3 million meters per second. But you know, atoms, just because they're hot, are going at hundreds of meters per second, and these are electrons, much lighter than atoms, that have been accelerated by a 5,000 volt discharge tube. So actually 2.3 times 10 to the 6 meters per second is not fast at all. If there were no atoms in there and we were accelerating our electron through a vacuum, then our electrons would be getting up to 10 to the 7. They'd be getting up to a significant fraction of the speed of light. So 10 to the 6, no problem. And of course we know that the discharge does this because I showed you a discharge tube that was producing H alpha, H beta, H gamma in the lab, and so that had to be electrons travelling faster than 2.3 times 10 to the 6 meters per second within that discharge tube to achieve that. Okay, so relatively typical exam question type for this sort of stuff. Okay, now mercury discharge tubes. You tend to think of mercury as a metal. You think, how can you have a discharge tube? But of course, it's a liquid, and it also vaporizes very easily. It's one of the reasons why we're not allowed to use mercury in schools anymore. Is that essentially you can sniff it, and you know that's part of the reason why people who used to work with mercury all the time went mad. The Mad Hatter. So mercury vaporizes quite easily. So if you put a drop of mercury into a vacuum tube and you've got a voltage squishy vacuum tube, you get a mercury vapor lamp. You get a mercury discharge tube. It does produce some spectral lines in the visible. Hopefully you can see that there, sort of 400 upwards. They're all in the visible, and you remember the spectral lines that I showed you on the very first slide. But you can also see that we've got quite a few in the ultraviolet as well. You can see, you know, one at about 380 there, another at 330, another at 310, etc. So we've got a whole set in the ultraviolet as well as the ones in the visible. And actually, it's not very efficient at producing the ones in the visible, but it's pretty efficient at producing the ones in the UV. And therefore, mercury discharge tubes are sometimes known as black lights. Because they're a good source of ultraviolet and not a great source of visible light, so most of their output is black, can't see it. Black lights are used in bars and nightclubs and things like that because there are various things that fluoresce, there are various things that glow under ultraviolet light. In particular, teeth glow under ultraviolet light, so you put a backlight into a dark nightclub and everybody's smiles glow. But also clothing, particularly white clothing, tends to glow under ultraviolet light because washing powders contain a thing called blue whitener. Which always makes me smile because it's a bit of a cheat. Blue whiteners absorb ultraviolet light and produce white light, and they do that to make your clothes look brighter than they really are. By any UV that happens to be about, they turn it into white, and oh, your shirt's really shining bright. So I say that black lights are used in nightclubs, things like that, because it has this odd effect of making certain bits of clothing glow and your teeth glow. And it, of course, if you've got this thing that's producing visible light and producing a lot of UV light pretty efficiently, then if you could turn that UV light into visible light, then you've got an efficient way of making visible light. And so that's what a fluorescent tube is. A fluorescent tube is a mercury discharge tube that's got a white coating on the inside of it, and the white coating, the phosphor, is absorbing the UV and re-emitting the UV as white light. Essentially, it's a blue whitener. It's the same as the stuff that's in your washing powder. It's absorbing all that UV that the mercury is nicely producing, and then it's emitting that alongside the visible light that the mercury already emits. And so that turns out to be an efficient-ish way of making visible light. It's annoying because they have a tendency to buzz. You have to have a really high voltage to get them started, and the starter motors tend to fail. Things that actually produce that high voltage, they tend to fail. and in comparison with LEDs, it's not that efficient. And so sort of industrial buildings like schools, once upon a time, were entirely lit by fluorescent tubes. Because it was the cheapest way to produce lots of white light. And there may still be fluorescent tubes around the school. I'm not entirely sure. There aren't any left in science anymore. They've all been taken out and replaced with LED panels. But there may be, over in some of the older blocks, like the new building, there might still be fluorescent tubes in there. But they don't stack up against LEDs. So once upon a time, they were a much better way of producing light than incandescent lamps. But today they've been superseded by LEDs. Anyway, just to go back to the how and the why, this is a spectrum. This is mostly in the visible rather than in the ultraviolet and visible, like the last one. You can see it goes a little bit beyond. We've got going above. Sorry, we've got going well under 400 on the UV side. But this is the little peaks that are marked, 3, 4, 5, 6. They're the original peaks that were in our original mercury discharge. And then in addition to this, we've got this broad peak given by our phosphor. And you can see that this, I've nicked it off Wikipedia, this picture is telling us that this particular phosphor has 2 different metal ions in it, which are responsible for the transitions. We've got antimony and manganese. But we don't care about that. All we care about is that the phosphor is giving us a peak, a very broad peak, not a narrow peak like an atom gives us. A phosphor is giving us a very broad peak in the sort of the oranges and the reds, so that the blues and the greens that we're getting already from the mercury, plus this orangey red that we're getting from the phosphor, mean that altogether it seems to it's enough to con our eyes into thinking we're receiving white light. And so mercury discharge combined with a fluorescent phosphor, efficient ways of producing light, and were once technologically really important. It's only been in this last maybe only 5 years that they've been totally superseded by LEDs. Before I move on, I'm just going to mention fluorescent and phosphor. There's a term called phosphorescence and there's a term called fluorescence, and I'm using this term phosphor. It's complicated. Phosphorescence and fluorescence are slightly different processes, and if I remember rightly, phosphorus is not phosphorescent, it's fluorescent. And so chemicals which glow when they're given energy, like our phosphor here, are fluorescent. I think I've got that right. Anyway, don't worry about the terms. You're not going to get penalised for them badly in the exam. Well, what else do I need to do before I go on? Well, I've seen 1 or 2 exam questions about fluorescent tubes and about how the light is produced from a fluorescent tube. I think that's unlikely that you'll get one on our new spec because, as I've repeated a few times now, the fluorescent tubes have been superseded by LEDs. But on the other hand, so have incandescent lamps, but that doesn't stop examiners writing questions about incandescent lamps. So, examiners are generally old. Mr. Widdop is the youngest examiner I've ever come across. And so the examiner might like his fluorescent tube questions or her fluorescent tube questions. So we'll just go through it. So the electrons are accelerated by the large field. When they strike the mercury atoms, they cause the mercury atoms to become excited via inelastic collision. When the mercury de-excites, we get some visible photons, but we also get some UV photons. And the UV photons are absorbed by the phosphor, exciting the compounds within the phosphor. And then when the electrons drop back down so that the phosphor goes back into its ground state, then the photons which were emitted as a result of that process are in the visible. so that our ultraviolet photons are turned into visible light. And if you choose the right phosphor to be mixed in with the light that's already being emitted by the mercury in the visible region, then you can get white light being produced by the discharge tube. One thing I might just point out there is one of the problems I get when people are writing about this, when students are writing about this stuff, is that, and it's true for the photoelectric effect, it's true for this stuff, is that the energy level diagrams that we've been drawing, you know, the potential well for the metal, the energy level diagrams we've been drawing here for our hydrogen, of course, are incredibly similar concepts. It's the same stuff. So you guys get them confused in your head. The technical teaching term, if no one cares, is a schema. You build them into the same schema. The trouble is that within a compound, within a solid, you get bands, you get ranges of energies that the electrons can be at, and you get more complicated things going on. Not all of the photon energy has to go into promoting the electrons. Some of it can go into just heating up the material. You know, not all of the electron energy has to come back out as the photon. Some of it can come out as heating up the material. So when we have light being emitted by a phosphor, we don't get a single narrow peak. We get this great big wide peak that you can see here in this picture for the manganese iron, for example. And that's because, you know, all sorts of other processes can happen in there because it's a solid. And so you've got to be careful in your language, because for a solid, our electrons are not at single energy levels. They're in bands, and more stuff can happen than just photons. On the other hand, when we're talking about atoms, single energy levels are all that's allowed. Nothing else is allowed. Single energy levels, effectively infinitely narrow energy levels, that's all that's allowed. And so you've just got to be a little bit careful about your language. I guess most examiners would allow it to slip by, but if you get an examiner that's a pedant like me, then they're going to get cross if you're using the word energy levels about solids, or, you know, bands about atoms. So energy levels for atoms are narrow lines. Only those particular energy levels are possible. Energy levels for, as soon as you get into even a molecule, they become slightly broader. As soon as you get into a solid, it becomes really broad. You don't get single peaks anymore in your spectra. You get these broad things that you're looking at in this picture right here for our halo phosphate phosphor. Okay, not an important point. I suspect a lot of examiners will let it go by, but if you can separate the two in your heads, then you've understood this math much better. Okay, summary for both lessons. You know, please, I'm not going back over this again in class, so you know, because we've got to move on. Please make sure that you have, at the very least, this stuff written down. I'm hoping you've written down a whole lot more than that. That you've been being proactive, and you've been pausing these lessons, and you've been writing down quite a lot of stuff as we've been going along. But at the very least, have written down what I've got coming up on the summary now. So energy level diagrams can be drawn for atoms, where each level represents an orbital. Ground state is the lowest energy, and that's n equals 1. Hydrogen, being the simplest, is the most common to turn up in exam questions. So 90% of exam questions, the energy level diagram that turns up will be 13.6 eV, will be ground state, or 22 times 10 to the minus 18 joules. And the energies are most often in EV, but watch out for them trying to give them to you in joules, because they know you're expecting them in EV. So if they want to make the exam question just a touch harder, you know, if they've looked at it and they decide they've not got enough hard questions in there, then an easy way to make one of these questions harder is to put it into joules, because you're expecting EV. Atoms can be excited so that their electrons move up into the higher levels. The most common way of exciting the atom is via inelastic collision with external electrons that are being accelerated in a discharge tube. An emission spectrum is formed by those photons emitted as the atoms de-excite back to their ground state, either directly or in steps, as we saw in the question that we did earlier on. It could have gone directly down and produced a big UV photon, or go in 2 steps and produce a visible photon and a UV photon. Questions can involve you being asked to explain the processes, especially how an emission spectrum forms with those very narrow lines. I went through how to answer that question. And calculation questions are usually to find the wavelengths of the emitted photons, and we had a look at that in the very first of these videos. Calculations can also be to find the energies and speeds of the colliding electrons, not just find out what the minimum speed is, the question that we did, but I've also seen ones where they say that electrons moving this fast, is it able to do an inelastic collision, or is it going to do an elastic collision? So you've got to work out what the K of the electron is and work out if that's enough to make an electron jump up to a higher energy level. And mercury-based fluorescent tubes were once technologically important, and so if our examiner is elderly, they may well like to still include them in exam questions. So we've just touched on it. How important it is to your revision, I'm afraid I don't know. Okay, I think that's done.